Imagine you have a bottle of acetaldehyde. It's a simple molecule, just two carbons, a double-bonded oxygen, and a few hydrogens. On its own, it's relatively stable. But what happens if we drop in a bit of sodium hydroxide? Suddenly, these identical molecules start seeking each other out, linking up to form something much more complex. This is the Aldol condensation, and the secret to how it works lies in a single, surprisingly acidic hydrogen atom. Let's look at our acetaldehyde molecule. Notice the carbon double bonded to the oxygen, that's the carbonyl group. It's greedy for electrons, pulling them away from the neighboring carbon, which we call the alpha carbon. This makes the hydrogens attached to that alpha carbon slightly loose. When we introduce sodium hydroxide, the hydroxide ion acts like a chemical scout looking for a proton to grab. As you can see here, it snatches one of those alpha hydrogens. This leaves the acetaldehyde molecule with a negative charge on its carbon. We call this an enolate ion. Now usually, carbon hates carrying a negative charge, but look at how the charge can flow up onto the oxygen atom through resonance. This stability is exactly what allows the reaction to begin. Now, here is the key insight. Because that enolate carbon is negative, it's looking for something positive to attack. And it finds it in a second, neutral molecule of acetaldehyde. Watch what happens when they collide. The negative carbon of our first molecule strikes the carbonyl carbon of the second. In an instant, a new carbon-carbon bond is forged. This is a massive moment in organic chemistry. We've just grown the carbon skeleton. We now have a single, larger molecule, but the oxygen on the second acetaldehyde is currently carrying a negative charge. It's an alkoxide. To steady itself, this oxygen reaches out and grabs a proton from a nearby water molecule. At this stage, we have what's called an aldol, a name born from the fact that the molecule contains both an aldehyde and an alcohol group. But we aren't quite finished. If there's even a little bit of heat, the molecule decides to slim down. Another hydroxide ion comes in and takes a second alpha hydrogen, and the molecule kicks out a hydroxide group entirely. Notice what's left behind, a brand new double bond. We've gone from two simple fragments to a conjugated enal, specifically crotonaldehyde. Looking at this final structure, it's easy to get lost in the arrows and the ions, but step back for a moment and consider the elegance of it. By simply shifting a single proton, we transformed a common base into a tool that stitches small molecules into larger ones. The Aldol condensation isn't just a recipe to memorize, it's a masterclass in how molecules use their own internal tension to build something new. In the world of synthesis, it's the ultimate bridge builder.